In the early 1970s, international motorsport stood at a critical crossroads of speed and regulation. As the dominance of monstrous prototype racers like the legendary Porsche 917 came to an abrupt regulatory end, the focus of European competition decisively shifted back toward production-based Grand Touring sports cars.
The Fédération Internationale de l'Automobile enforced strict Group 4 homologation rules, demanding a minimum production run of 500 road-legal units within 12 months. These technical regulations rewarded manufacturers who could transform high-volume road cars into uncompromising featherweight machines capable of enduring grueling long-distance circuit battles.
For Porsche, the timing could not have been more precarious or urgent. The standard 911S, while agile and beloved by privateers, was rapidly losing its competitive edge against heavily modified rivals like the Ford Capri RS 2600 and the increasingly potent BMW lightweight coupes. On the track, displacement and raw aerodynamic efficiency dictated the winners. The existing 2.4-liter flat-six engine struggled against larger multi-valve rivals on high-speed circuits like Monza, Spa-Francorchamps, and the Nürburgring, leaving Weissach engineers facing a desperate engineering deficit they could no longer ignore. Inside the executive offices at Zuffenhausen, newly appointed chairman Ernst was steering the company into a transformative era. Fuhrmann, an engineer of immense technical pedigree who developed the legendary four-cam engine, believed Porsche must either dominate motorsport comprehensively or withdraw to preserve its brand prestige. Led by racing director Peter Falk and chassis visionary Helmut Bott, the engineering division proposed an audacious solution. They envisioned an extreme, stripped-down variant of the 911, engineered specifically for Group 4 homologation, maximizing engine displacement, structural rigidity, and aerodynamic balance without compromise. However, this bold vision collided head-on with deep skepticism from the corporate sales and marketing departments. Building 500 raw, unrefined track specials was seen as an unacceptable financial gamble during a volatile global economy, increasingly threatened by impending fuel crises and tightening safety mandates. Company executives openly questioned whether affluent customers would pay a massive premium for a noisy, uninsulated 911 stripped of basic creature comforts. The fear of 500 unsellable sports cars rusting on dealership lots sparked intense, heated debates throughout the executive boardroom meetings. Despite severe corporate hesitation, Ernst backed his engineering team and greenlit the project with an iron fist. He recognized that racing success was the ultimate lifeblood of the Porsche brand, authorizing development under the strict mandate that all 500 homologation units had to be sold. The project was christened with the suffix RS, standing for Rennsport, the German word for racing sport. This designation was not merely decorative. It represented a relentless corporate philosophy aimed at shedding every single unnecessary gram of weight while extracting maximum mechanical efficiency from the platform. To elevate the project beyond a simple technical homologation exercise, Porsche decided to revive an illustrious name from its golden past. The Carrera moniker, originally earned through grueling victories in the legendary Carrera Panamericana road race during the 1950s, was proudly resurrected for the new machine. Combining Carrera with the Rennsport badge created an identity that resonated with pure motorsport nobility. The resulting 911 Carrera RS was conceived not as a compromise between road and track, but as an unapologetic thoroughbred racer that just happened to wear legal license plates on public roads. Under the direction of Bott and his engineering staff, weight reduction became an obsessive religion. Engineers systematically replaced standard steel panels with thinner gauge sheet metal, replaced heavy glass with lightweight Glaverbell windows, and discarded interior sound deadening, rear seats, armrests, and even the iconic passenger glovebox clock. Simultaneously, engine maestro Valentin Schäfer was tasked with unlocking unprecedented performance from the air-cooled flat-six architecture.
By boring out the cylinders to 90 millimeters and applying advanced Nikasil cylinder wall coatings, the team created the formidable 2.7-liter Type 911-83 power plant. Aerodynamics, a science often neglected in early sports car development, took center stage in the wind tunnel. Engineers discovered that rear-end high-speed lift could be conquered through an integrated rear spoiler, giving birth to the now immortal Ducktail, which drastically increased rear downforce and stability at high speeds. To placate the anxious sales division, Porsche formulated a clever two-tier customer offering. The hardcore M471 lightweight package was built purely for track purists, while the M472 touring version retained essential road equipment, offering grand touring comfort wrapped in the aggressive bodywork of a homologation special. In October 1972, the production-ready Porsche 911 Carrera RS 2.7 made its dramatic world debut at the Paris Motor Show. Its striking stance, bold Carrera side script, color-matched Fuchs alloy wheels, and radical rear Ducktail spoiler stunned the international automotive press. Any lingering skepticism inside Zuffenhausen evaporated almost overnight as the global response shattered every conservative sales projection. Within just a few short weeks of the Paris debut, the entire initial homologation run of 500 vehicles had completely and utterly sold out to eager enthusiasts worldwide. With demand reaching unprecedented heights, Porsche swiftly authorized additional production batches to fulfill customer orders and qualify for even more competitive racing classes. Ultimately, more than 1,500 Carrera RS units rolled off the assembly line, transforming an existential gamble into one of history's greatest triumphs. What began as a desperate struggle against homologation deadlines and internal boardroom doubt ultimately forged the quintessential road-legal sports car. The 1973 Carrera RS 2.7 permanently redefined the DNA of Porsche, setting an immortal engineering benchmark that remains legendary more than half a century later. At the very core of the legendary Carrera RS lies the Type 911/83 engine, a masterpiece of air-cooled engineering. Developed from the high-strung 2.4-liter 911S power plant, this newly conceived flat six represented the ultimate evolutionary zenith of the classic naturally aspirated magnesium crankcase architecture. To achieve a decisive leap in circuit performance, Porsche engineers recognized that displacement was paramount. They retained the robust die-cast magnesium alloy crankcase from the 2.4-liter unit, which provided exceptional structural rigidity while maintaining an astonishingly low dry weight, crucial for optimal rear weight distribution. The displacement increase to precisely 2,687 cubic centimeters was achieved by enlarging the cylinder bore to an unprecedented 90 millimeters. Engineers paired this generous bore with the proven 70.4mm stroke forged steel crankshaft, establishing an over-square geometry optimized for rapid revving and sustained high RPM operation. Expanding the cylinder bore to 90mm pushed the physical limits of the compact engine casing. With minimal space remaining between the individual finned cylinders, heat dissipation and dimensional stability under extreme thermal stress became the primary hurdles that demanded radical metallurgical innovation. Porsche resolved this critical thermal challenge by pioneering the application of advanced nickel silicon carbide coatings directly onto the aluminum cylinder walls. This cutting-edge surface treatment drastically reduced internal frictional losses, eliminated the need for heavy cast iron liners, and delivered vastly superior heat conduction during endurance racing. Within these ultra-hard cylinder bores operated bespoke forged aluminum alloy pistons engineered by Mala. Featuring carefully sculpted crowns and shortened skirts, these lightweight components minimized reciprocating mass, allowing the engine to accelerate freely toward its towering 7,300 RPM redline without risking catastrophic mechanical failure. The static compression ratio was meticulously set at 8.5 to 1. This strategic figure allowed the high-output flat six to extract explosive combustion energy while maintaining absolute reliability across varied climatic conditions, easily tolerating standard 98 RON commercial premium fuel without harmful detonation. Cylinder head architecture received equal attention, featuring CNC-machined hemispherical combustion chambers and extensively ported intake tracts. Airflow dynamics were meticulously simulated and polished, ensuring maximum volumetric efficiency across the entire power band while preserving the crisp velocity essential for instant low-end throttle response. The valve train utilized enlarged intake and exhaust valves, actuated by single overhead camshafts per bank. The exhaust valves featured hollow sodium-filled stems, a direct motorsport transfer that rapidly wicked away intense combustion heat toward the cylinder heads to prevent thermal fatigue under continuous full-throttle loads. Aggressive camshaft profiles derived directly from the revered 2.4-liter 911S governed valve timing. Featuring generous duration and substantial valve overlap, these camshafts were optimized to exploit natural acoustic resonance within the intake plenums, supercharging the cylinders mechanically at elevated engine speeds. Fuel delivery was entrusted to a sophisticated Bosch mechanical multi-plunger injection system, designated the PED-6KL pump. Driven directly by the left-hand camshaft via a dedicated toothed belt, this intricate mechanical computer delivered precisely timed fuel charges directly into each individual cylinder intake port. Inside the Bosch pump, a complex three-dimensional space cam continually calculated fuel metering. By mechanically measuring throttle valve position, engine speed, ambient atmospheric pressure, and operating temperature, the system supplied razor-sharp air-fuel mixtures without relying on any primitive electronic sensors or microprocessors. 6 individual butterfly throttle bodies were fed by tuned plastic intake trumpets and equal-length intake runners. This individual runner configuration minimized intake turbulence and delivered instantaneous throttle response, reacting to the slightest depression of the accelerator pedal with immediate, unhesitating forward thrust. Compared to traditional carburetors or nascent electronic injection systems of the era, the mechanical fuel injection proved vastly superior. It maintained flawless fuel atomization during violent lateral cornering forces and heavy braking, ensuring uninterrupted power delivery on demanding circuits without stalling or leaning out. Engine longevity was safeguarded by an intricate dry sump lubrication system utilizing a high-capacity internal scavenge pump, a massive external oil tank, and an auxiliary front-mounted oil cooler regulated temperatures, keeping the magnesium engine perfectly stabilized even during the hottest 24-hour endurance contests. The resulting performance figures were staggering for a production sports car in 1972. The Type 911/83 developed an impressive 210 horsepower at 6,300 RPM, achieving a specific output of over 78 horsepower per liter, an astonishing engineering benchmark for an air-cooled 2-valve per cylinder road engine. Equally remarkable was the torque curve, which peaked at an authoritative 255 Nm at 5,100 RPM. More importantly, over 90% of this muscular pulling power was readily available from below 3,000 RPM, endowing the Carrera RS with immense, flexible mid-range acceleration. Despite its purebred racing pedigree, the Type 911/83 engine demonstrated astonishing everyday civil manners. It started reliably in freezing conditions, settled into a smooth idle, and pulled cleanly from low speeds without fouled spark plugs or the temperamental coughing common to competition-tuned machinery. Furthermore, the remarkably clean combustion process enabled the Carrera RS to easily pass increasingly stringent European exhaust emissions regulations. Porsche proved to the world that uncompromising motorsport performance and responsible environmental compliance could harmoniously coexist through rigorous mechanical precision and superior thermal design. The Type 911/83 Flat 6 stood as the pinnacle of mechanical purity, capturing the essence of naturally aspirated power. Its intoxicating acoustic soundtrack, razor-sharp throttle precision, and unbreakable mechanical durability permanently cemented its reputation as one of the finest internal combustion engines ever created.
Beyond raw displacement and precise fueling, the true genius of the Carrera RS engine resided within its groundbreaking material science. Porsche engineers dared to push metallurgical boundaries far beyond conventional automotive standards, pioneering advanced alloys and revolutionary surface treatments to conquer extreme thermal and physical stresses. Traditional air-cooled cylinder architecture had long depended on heavy cast-iron sleeves pressed into aluminum-finned barrels. However, these restrictive iron liners created a severe thermal barrier, impeding heat transfer, adding undesirable reciprocating bulk, and strictly limiting the maximum achievable cylinder bore diameter within the engine casing. To overcome these mechanical bottlenecks, Porsche collaborated closely with German engineering specialist Molly to deploy an exotic aerospace coating known as Nikasil. First proven under the brutal racing conditions of the mighty 917 prototype, this revolutionary process represented a total paradigm shift in high-performance engine manufacturing. Nikasil, a proprietary acronym for nickel silicon carbide, was an ultra-hard composite coating applied via an advanced electrolytic deposition process. Millions of microscopic silicon carbide ceramic particles measuring less than 3 microns across were uniformly dispersed throughout an extraordinarily durable nickel matrix directly onto the bare aluminum barrel. By plating this ultra-thin composite layer directly onto the all-aluminum cylinder walls, engineers completely eliminated the traditional cast-iron liners. This metallurgical breakthrough allowed the internal cylinder diameter to expand outward without sacrificing barrel wall thickness, effectively granting the Flat Six unprecedented displacement without adding structural mass. Thermal efficiency was transformed instantaneously because aluminum shares an identical thermal expansion coefficient throughout the entire cylinder assembly. Without the disruptive thermal resistance of an iron interface, combustion heat flowed seamlessly from the cylinder bore directly into the surrounding cooling fins, dramatically accelerating thermal dissipation. Under grueling full-throttle racing conditions, the Nikasil-plated cylinders ran noticeably cooler and maintained absolute circular geometry under intense thermal stress. The superior heat conductivity prevented localized hotspots, virtually eliminating the risk of catastrophic piston seizure and drastically reducing the engine's susceptibility to destructive high RPM detonation. At a microscopic level, the exposed silicon carbide crystals functioned as an exceptionally hard, wear-resistant friction surface. Meanwhile, the surrounding nickel matrix created tiny, natural microscopic oil reservoirs that trapped lubricating oil film, drastically minimizing boundary friction between the piston rings and the rapidly moving cylinder walls. The extraordinary surface hardness of Nikasil, registering roughly 5 times harder than standard cast iron, meant that bore wear was virtually non-existent. Even after hundreds of hours of relentless competition, cylinder dimensions remained within factory tolerances, ensuring consistent compression pressures and maximum ring seal throughout grueling endurance races. Because the forged aluminum pistons and all-aluminum Nikasil cylinders expanded at nearly identical rates when heated, engineers could specify remarkably tight piston-to-bore clearances. This tight tolerance reduced piston slap during cold starts, improved oil control, and maximized combustion chamber sealing for instantaneous throttle response and superior thermodynamic efficiency. The reduction in internal friction translated directly into measurable horsepower gains and reduced mechanical drag across the entire operational rev range. Less energy was wasted as parasitic frictional heat, allowing the Type 911/83 engine to convert explosive combustion pressure into pure, unadulterated rotational force with breathtaking ease. Complementing the advanced cylinder technology was the featherweight structural foundation of the engine, the high-pressure die-cast magnesium alloy crankcase. While most contemporary sports car manufacturers relied on heavy cast iron or traditional aluminum, Porsche fully embraced magnesium to execute their uncompromising lightweight philosophy. The specialized magnesium alloy, enriched with trace amounts of aluminum and zinc, offered an extraordinary strength-to-weight ratio, unmatched by any mass production material of the era. Weighing approximately 1/3 less than aluminum and nearly 80% less than cast iron, it established an astonishingly light crankcase assembly. Manufacturing these complex crankcase halves required sophisticated high-pressure die casting techniques executed under strict environmental controls. Molten magnesium was injected at immense speed and pressure into precision steel molds, ensuring an ultra-dense, homogeneous crystalline structure entirely free from structural porosity or internal microscopic metallurgical defects. This state-of-the-art casting process produced remarkably thin, yet exceptionally rigid structural walls throughout the entire crankcase architecture. Complex oil passages, scavenge galleries, and mounting bosses were seamlessly integrated into the casting itself, eliminating unnecessary external plumbing and further trimming vital grams from the overall engine package. Removing substantial mass from the extreme rear of the chassis was crucial for vehicle dynamics. By paring engine weight down to the absolute physical minimum, the magnesium crankcase significantly reduced the rear axle polar moment of inertia, directly enhancing cornering agility, steering precision, and braking stability on the track. Harnessing magnesium required meticulous thermal engineering due to its comparatively high coefficient of thermal expansion. Porsche designers meticulously calculated the dimensional growth of the crankcase at operating temperature, engineering specific bearing journal clearances and main bearing saddle reinforcements to prevent distortion under high thermal and mechanical loads. To withstand the severe torsional loads generated by the high-torque flat six, external structural webbing and internal reinforcing ribs were cast directly into the crankcase walls. These strategic stiffening ribs distributed firing impulses evenly across the main bearing supports, preventing block flex and ensuring absolute crankshaft alignment. To safeguard the magnesium against ambient galvanic corrosion and harsh road grime, Porsche subjected every raw crankcase casting to specialized chemical passivation baths. A distinctive golden olive chromate conversion coating was chemically bonded to the metal, creating a protective barrier that preserved structural integrity in humid and salty environments. The harmonious fusion of electroplated Nikasil cylinders and high-pressure die-cast magnesium formed a legendary metallurgical tour de force. Through relentless experimentation and radical material science, Porsche unlocked an unprecedented balance of featherweight construction, unmatched thermal efficiency, and unbreakable durability that defined the Carrera RS legend. While the mechanical heart of the Carrera RS generated exhilarating speed, taming that raw velocity exposed a fundamental aerodynamic challenge. The iconic teardrop fastback silhouette of the classic 911, although visually timeless, functioned dangerously like an aircraft wing at extreme speeds on high-speed circuits. As air flowed rapidly over the curved roofline and sloping rear deck lid, low pressure developed over the rear axle. This severe aerodynamic lift caused the rear tires to lose crucial contact with the tarmac, turning high-speed cornering and braking into a harrowing test of survival. Drivers frequently complained that the front end felt featherweight and disconnected at speeds exceeding 100 miles per hour. The combination of an engine hung behind the rear axle and massive aerodynamic lift threatened to induce violent oversteer during high-speed directional changes. Determined to conquer these treacherous aerodynamic forces, chassis engineer Tilman Broadbeck and aerodynamicist Hermann Burst began intensive testing inside the Weissach wind tunnel. They recognized that mechanical grip from wider tires and stiffened anti-roll bars was entirely insufficient without mastering the invisible airflow surrounding the vehicle. Working methodically with scale models and full-sized prototypes, Burst and Broadbeck applied woolen tufts and specialized pressure sensors along the bodywork. They discovered that airflow remained rigidly attached to the downward-sloping rear window, creating a massive vacuum pocket that lifted the rear axle upward. The engineering duo experimented with crude sheets of metal, wood, and modeling clay attached directly to the trailing edge of the engine cover.
they sought a device that could effectively break the air separation bubble and generate stabilizing downward force without creating catastrophic aerodynamic drag. Their relentless wind tunnel trials led to an unconventional, upswept fiberglass lip grafted onto the rear deck lid. This distinctive upward flick altered the local pressure distribution completely, creating a high-pressure zone directly over the tail while cleanly detaching the boundary airflow behind the vehicle. Inside the development workshop, this radical aerodynamic appendage was promptly nicknamed the Berzel, the German word for a bird's rump or ducktail. While factory stylists initially criticized its unconventional shape, the empirical data gathered from the wind tunnel instrumentation proved utterly undeniable. The Ducktail slashed rear aerodynamic lift by an astonishing 75%, transforming the unsettled tail into a rock-solid platform at racing speeds. By disrupting the suction effect over the rear deck, it anchored the driven wheels firmly against the asphalt under heavy acceleration. Even more extraordinary was the effect on overall aerodynamic drag. Instead of acting as an air brake, the carefully contoured ducktail filled the turbulent low-pressure wake trailing the car, actually reducing the drag coefficient slightly and permitting a higher terminal velocity down long straights. Furthermore, the Ducktail dramatically optimized thermal management for the air-cooled Type 911-83 power plant. By forcing a portion of the attached airstream directly downward through the horizontal engine lid grille, it significantly increased cooling airflow across the fin cylinders and oil cooler. However, stabilizing the rear end solved only half of the aerodynamic equation. The newfound rear downforce created an alarming pitch imbalance, pivoting the car along its wheelbase and exaggerating high-speed front-end lift, which compromised crucial steering precision and front tire grip during rapid turn-in. To establish complete aerodynamic equilibrium, Burst and Broadback developed an aggressive front chin spoiler integrated into the lower fiberglass valance. This deep front air dam extended downward, effectively blocking high-pressure ambient air from rushing underneath the chassis and creating destabilizing underbody lift. The front chin spoiler reduced front axle aerodynamic lift by over 30%. Simultaneously, it diverted fresh cooling air through dedicated ducting toward the front-mounted auxiliary oil cooler and ventilated front disc brakes, ensuring absolute thermal and braking stability under punishing circuit conditions. Working in absolute harmony, the deep front chin and the iconic rear ducktail formed the world's first coordinated production car aerodynamic package. This paired system kept the entire vehicle flat and neutral, eliminating unpredictable aerodynamic balance shifts between high-speed straightaways and high-G braking zones. The real-world benefits were instantaneous during circuit testing at the Nürburgring and Paul Ricard. Racing drivers reported that the Carrera RS tracked with razor-sharp precision through high-speed sweepers, allowing them to carry significantly higher entry speeds with total psychological and mechanical confidence. Beyond the track, Porsche faced formidable bureaucratic hurdles gaining road homologation for the radical spoiler. German vehicle licensing authorities initially deemed the protruding ducktail a potential pedestrian hazard, demanding exhaustive safety demonstrations before finally granting official road certification for regular street use. When the car debuted publicly, the striking combination of functional spoilers and widened rear fenders stunned the automotive establishment. What began as a pure scientific solution to aerodynamic instability instantly became the definitive visual signature of high-performance German sports car engineering. By proving that purposeful aerodynamic development could enhance downforce, reduce drag, and improve engine cooling simultaneously, Porsche rewrote the rulebook of sports car design. The ducktail demonstrated that unseen air currents could be harnessed as an invisible, decisive mechanical advantage. The legend of the ducktail endures as an indelible milestone in automotive history. Born from empirical wind tunnel rigor and relentless engineering courage, it transformed an inherently unstable rear-engine chassis into an immortal, track-dominating weapon whose aerodynamic legacy still echoes across the generations.
To satisfy both track purists and discerning street drivers, Porsche devised two distinct factory option codes. Option M471 created the uncompromising sport lightweight, while Option M472 delivered the civilized touring package, establishing a fascinating contrast between raw competition machinery and luxurious grand touring comfort. The M471 lightweight stood as the purest physical manifestation of the Rennsport ethos, stripped of every non-essential component. Engineering teams treated excess mass as an absolute enemy, systematically analyzing every structural stamping, fastener, and cabin fitting to extract maximum mechanical agility from the chassis. At the structural foundation of the lightweight lay bespoke ultra-thin body paneling produced by Belgian specialist Glaverbel. While conventional production cars utilized heavier gauge steel, Porsche commissioned specialized sheet metal stamped to a thickness of just 0.7 millimeters, substantially reducing baseline body mass. This fragile yet featherweight sheet metal formed the roof panel, front luggage compartment lid, and exterior floor stampings. By substituting standard steel with these ultra-thin panels, engineers trimmed crucial kilograms directly from the structural shell, though factory workers had to handle the delicate pressings with extraordinary care. Glazing underwent an equally radical technical revision to lower the vehicle's center of gravity. Porsche replaced standard heavy laminated windshields and thick tempered glass with custom lightweight Glaverbel glass, measuring just 3 millimeters thick on the side quarter windows and the iconic wraparound rear windscreen. The weight savings achieved through thin glass directly improved dynamic stability through high-speed corners. By removing substantial mass from the upper greenhouse area, engineers drastically reduced the pendulum effect and lateral body roll, allowing the rear-engine chassis to change direction with surgical immediacy and total poise. External body fittings were completely re-engineered using advanced lightweight materials borrowed directly from competition racing. The heavy pressed steel front bumper and rubber overriders were discarded in favor of a single-piece molded fiberglass front apron that integrated the aerodynamic air dam and auxiliary oil cooler intake. At the rear, the conventional steel bumper assembly and heavy bumper guards were replaced by featherweight fiberglass moldings. Even the signature Ducktail engine cover was formed from a composite fiberglass skin permanently bonded to an inner aluminum or steel frame, shaving vital mass from behind the rear axle. Beneath the vehicle, Porsche eliminated the heavy bituminous undercoating and thick polyvinyl chloride seam sealers normally applied to road cars. While this decision sacrificed long-term corrosion resistance in harsh weather, it immediately shed several crucial kilograms of dead weight from the lower floor pan assembly. Step inside the M471 cockpit, and the obsessive weight-saving diet became immediately apparent to the driver. All heavy acoustic deadening pads, horsehair sound insulation, and thick rubber backing were ruthlessly banished from the bulkhead, transmission tunnel, and inner quarter panels, exposing bare painted metal throughout. In place of plush, multi-piece wool carpeting, workers glued ultra-thin black needle felt material directly to the bare floorboards. The lack of acoustic insulation allowed the visceral mechanical symphony of the air-cooled flat six, gearbox whine, and gravel spray to reverberate directly inside the cabin. The standard door panels were completely discarded and replaced with flat, single-ply black vinyl cards without padded armrests or map pockets. To further save weight, engineers eliminated the heavy metal door release linkages, installing simple black leather pull straps that quickly became an enduring motorsport icon. Manual window regulators were stripped of heavy internal spring balances and replaced with minimalist plastic crank mechanisms. On the most extreme competition-bound examples, fixed plastic side windows with sliding vent panels replaced the wind-up glass entirely, eliminating the internal window regulator mechanisms and hardware altogether. The dashboard was stripped of non-essential instrumentation and decorative trim, deleting the iconic analog clock in favor of a blank plastic blanking plug. The glove box lid was removed or replaced with an ultralight cover, and the passenger side sun visor was deleted from the cabin headliner.
Factory seating received a radical motorsport transformation, discarding the heavy-sprung, leather-upholstered reclining road seats. In their place stood deep Recaro racing bucket seats, featuring lightweight fiberglass-reinforced shells, trimmed in simple black vinyl with corduroy center inserts to hold the driver securely during high lateral cornering. The rear seating area was completely eliminated, leaving a bare, carpet-covered shelf devoid of folding seat backs, squabs, or safety harness hardware. This modification alone removed substantial mass from the rear axle area, improving both interior luggage capacity for racing equipment and the chassis balance.
Even small hardware details underwent fanatical scrutiny, with aluminum engine lid supports replacing heavy steel torsion springs. The front hood was secured with lightweight rubber latches, and the heavy metal battery was swapped for a smaller, lightweight unit tucked neatly inside the front compartment. Through this fanatical engineering diet, the M471 Sport Lightweight achieved an astonishing homologation curb weight of just 960 kilograms. This featherweight figure unlocked an electrifying power-to-weight ratio, allowing the 210 horsepower engine to launch the car with violent urgency. For customers desiring grand touring civility, the M472 Touring Package reinstalled the full 911S interior appointments. The Touring retained sound deadening, standard steel bumpers, reclining sport seats, thick carpeting, and power accessories, bringing the total curb weight up to a still impressive 1,075 kilograms. The coexistence of the M471 Lightweight and M472 Touring perfectly illustrated the versatile genius of Porsche engineering. Whether ordered as an uncompromising track weapon or a sophisticated high-speed grand tourer, each machine celebrated the purest spirit of performance through meticulous, purpose-driven craftsmanship. While engine output and weight reduction formed the foundation of performance, mastering the chassis was paramount to converting mechanical energy into surgical racetrack speed. Engineers in Weissach systematically reevaluated every suspension component, creating an exceptionally responsive platform capable of harnessing the explosive power of the flat-six engine. At the front, the independent McPherson strut configuration received extensive structural reinforcement and meticulous geometry revisions. Paired with longitudinal torsion bar springs, the front suspension was recalibrated to maintain razor-sharp turn-in authority, ensuring the front tires maintained an uncompromising contact patch under aggressive high-speed cornering maneuvers on demanding road circuits. The rear suspension utilized an independent semi-trailing arm layout connected to transverse torsion bars, engineered specifically to manage the rear engine weight distribution. Engineers re-indexed the torsion bars to optimize ride height, lowering the roll center and dramatically improving high-speed directional stability during rapid weight transfers through demanding chicanes. Damping duties were entrusted to custom Bilstein gas-pressurized monotube dampers, a revolutionary upgrade over conventional twin-tube hydraulic units of the era. High-pressure nitrogen gas prevented oil cavitation and foaming under grueling track conditions, providing instantaneous damping response and unyielding tire control over continuous high-frequency undulations and rough apex curbs. These bespoke Bilstein dampers delivered consistent, fade-free resistance throughout grueling endurance competitions, maintaining precise rebound and compression rates under intense thermal loading. The transition to advanced gas-pressurized technology dramatically minimized unwanted body float, allowing racing drivers to place the car with absolute precision along tight apexes and high-speed crests. To drastically reduce chassis lean without sacrificing ride compliance, engineers upgraded the torsion bar diameters across both axles. The stiffer springing rates effectively restricted excessive squat under hard acceleration and curbed front-end dive under heavy braking, preserving the delicate dynamic equilibrium of the lightweight competition chassis during aggressive transitions. Complementing the refined springing rates were substantially thicker tubular anti-roll bars, measuring 18 millimeters at the front and 19 millimeters at the rear. These stiffened anti-roll bars worked in flawless harmony, virtually eliminating excessive body roll while allowing the suspension arms to articulate freely over asymmetric road imperfections.
To withstand immense lateral cornering forces, the rear trailing arms were fortified with heavy-duty reinforcements at critical structural pivot points. This added structural rigidity prevented unwanted toe and camber deflection under heavy throttle loading, eliminating the treacherous snap oversteer that had previously plagued earlier iterations of the rear-engine sports car. Every chassis mounting bushing was upgraded to higher durometer rubber compounds, eliminating mechanical compliance and sharpening transient steering response. This deliberate stiffening transmitted unfiltered kinematic feedback directly to the driver, transforming subtle tire adhesion changes into crystal-clear sensory information through the steering wheel and the driver's seat. Braking performance was elevated to motorsport standards through internally ventilated disc brakes derived from the revered 911S. Featuring two-piston cast-iron calipers clamped onto thick, vented rotors, the braking system delivered exceptional thermal capacity, resisting heat fade during repeated decelerations from speeds exceeding 200 kilometers per hour. Carefully calibrated hydraulic proportioning valves distributed braking force evenly between axles, preventing rear-wheel lockup under severe deceleration. Dedicated front cooling ducts channeled cold ambient air directly into the brake assemblies, effectively dissipating kinetic energy and maintaining a rock-solid, predictable pedal feel, even during grueling multi-hour endurance races. Perhaps the most revolutionary dynamic chassis innovation was the bold decision to specify staggered wheel widths across the front and rear axles. Breaking away from traditional uniform fitments, this pioneering configuration marked the first time a production sports car featured wider wheels on the driven rear axle. The legendary 5-spoke wheels were manufactured by Otto Fuchs using an advanced drop forging process from seamless aerospace-grade aluminum. This sophisticated metallurgical technique produced wheel centers and rims of extraordinary tensile strength and featherweight lightness, substantially reducing unsprung mass to optimize suspension compliance and instantaneous acceleration response on uneven asphalt. On the front axle, engineers fitted 6-inch wide Fuchs forged alloy wheels, mounted with low-profile performance radial tires. This specific dimension was chosen to preserve delicate steering lightness and prevent excessive front-end tramlining, enabling the front tires to dart eagerly into tight apexes with razor-sharp feedback and unwavering mechanical grip. At the rear, the wheel width was widened to an unprecedented 7 inches, shod with substantial high-performance radial tires. This wider rear footprint delivered massive mechanical traction under full throttle, effectively planting the rear engine mass and maximizing the transfer of explosive engine torque directly into pure forward acceleration. The wider rear rubber radically cured the notorious pendulum effect handling characteristics inherent to the classic rear engine layout. By providing superior lateral grip at the driven wheels, the staggered fitment permitted higher corner entry and exit speeds, allowing the chassis to track cleanly through sweepers without unexpected rear breakaway. Accommodating the massive 7-inch rear Fuchs wheels required an aggressive physical modification to the standard rear quarter panels. Factory metalworkers painstakingly welded widened steel flare extensions directly onto the production steel bodywork, creating generous internal wheel clearance while giving the vehicle its unmistakably muscular and predatory road presence. These hand-finished rear flares expanded the overall rear body width by 42 millimeters, creating the iconic sculpted silhouette that defined the RS identity. Beyond visual aggression, the widened rear track substantially increased lateral stability, providing a wider mechanical stance that resisted body roll and maximized high-speed cornering grip. The unassisted rack and pinion steering rack was meticulously calibrated, communicating every pebble and surface texture with unadulterated fidelity. Because the lightweight front end carried minimal static mass, the steering remained remarkably light, surgical, and communicative, allowing drivers to execute microscopic line corrections with instinctive confidence and fingertip precision. The harmonious integration of gas-pressurized damping, fortified suspension links, and revolutionary staggered Fuchs wheels forged an invincible handling platform.
Through uncompromising dynamic engineering, the Carrera RS established a benchmark in chassis poise, elevating driver engagement to an art form that forever redefined the limits of sports car performance. With the essential homologation threshold successfully surpassed, Porsche engineers immediately unleashed the ultimate evolutionary expression of the RS platform onto the global motorsport stage. This radical transformation gave birth to the fearsome Carrera 2.8 RSR, an uncompromising Group 4 thoroughbred engineered specifically to conquer international endurance championships. At the mechanical heart of this new racing weapon sat the Type 911/72 competition engine, enlarged to 2,806 cubic centimeters. By pushing the cylinder bore to an extreme 92 millimeters while retaining the standard forged crankshaft, engineers unlocked immense volumetric efficiency, allowing the air-cooled flat six to breathe with terrifying ferocity. To optimize high RPM combustion stability, the 2.8 RSR adopted a sophisticated twin-plug cylinder head ignition system powered by twin Bosch distributors. Combined with aggressive high-lift camshafts, enlarged titanium valves, and recalibrated mechanical fuel injection, the naturally aspirated power plant generated an astounding 300 horsepower at 8,000 RPM. Taming this explosive output required radical aerodynamic and structural adaptations that dramatically altered the visual stance of the 911. Hand-formed composite fiberglass fender flares were riveted over dramatically broadened wheel arches, accommodating massive 9-inch front and 11-inch rear center-lock lightweight alloy wheels wrapped in ultra-wide racing slicks. Beneath the widened bodywork, the chassis was fortified with race-proven hardware directly derived from the world-conquering 917 prototype. Massive 4-piston finned aluminum brake calipers and internally ventilated cross-drilled rotors provided immense stopping power, while fully adjustable coil-over helper springs complemented the torsion bars to deliver surgical apex control. The baptism of fire for the new competition machine arrived in February 1973 at the grueling 24 Hours of Daytona. Porsche delivered two brand-new 2.8 RSR chassis to privateer teams, with Peter Gregg and Hurley Haywood representing Brumos Racing, alongside Penske Racing drivers Mark Donohue and George Fulmer. Facing heavily favored sports prototype entries from Matra, Mirage, and Ferrari, the production-based Porsche entrants were widely dismissed as mere class contenders. Yet the punishing high-banked turns and infield twists of the Daytona International Speedway began systematically breaking the complex, fragile, purpose-built prototype machinery as temperatures plummeted overnight. While rivals suffered catastrophic mechanical failures, the Brumos 2.8 RSR operated with bulletproof consistency, climbing relentlessly through the overall standings. Even when a stray bird shattered the passenger-side windshield at speed, Haywood calmly adapted, maintaining blistering lap times without sacrificing vital seconds in the pit lane. Against all conventional wisdom, Peter Gregg and Hurley Haywood crossed the finish line to claim a sensational overall victory at Daytona. A production-derived Grand Touring car had conquered the world's finest prototypes, establishing one of the most stunning upsets in endurance racing history and electrifying the global motorsport community. That sensational momentum surged across the Atlantic to the sun-drenched, perilous mountain roads of Sicily for the 57th Targa Florio. As the final official World Championship running of the historic road race, the legendary event demanded supreme agility and unyielding mechanical durability across thousands of tortuous mountain curves. Factory support arrived under the iconic Martini Racing banner, fielding an experimental RSR driven by Dutch master Gijs van Lennep and Swiss ace Herbert Mueller. The treacherous 72-kilometer Circuito Piccolo della Madonnina presented broken asphalt, sheer drops, and unforgiving stone walls that punished the slightest driver miscalculation. Dedicated factory prototypes from Ferrari and Alfa Romeo set an unforgiving early pace, yet the punishing Sicilian terrain quickly extracted a devastating mechanical toll. Suspension failures and catastrophic crashes decimated the fragile prototype field, clearing a path for the rugged, perfectly balanced Martini Porsche to seize absolute control. Displaying superhuman precision over 11 grueling laps, Van Lennep and Mueller crossed the finish line to secure a historic overall victory. It marked Porsche's 11th and final overall triumph at the prestigious Targa Florio, forever cementing the rear-engine racer's reputation as an invincible giant killer on open public roads. Building upon this sensational momentum, Weissach engineers developed the definitive racing evolution for the 1974 season, the fearsome Carrera 3.0 RSR. Featuring an expanded 2,992 cubic centimeter power plant with an aluminum alloy crankcase, this ultimate evolution produced a towering 330 horsepower in naturally aspirated race trim. The 3.0 RSR showcased radical aerodynamic advancements, introducing deeply sculpted composite box flares and the monstrous whale-tail rear wing. This immense rear aerodynamic appendage featured integrated auxiliary oil coolers, stabilizing high-speed airflow over the wider rear tires while dramatically improving thermal management during long-distance circuit battles. Customer racing teams eagerly acquired the 3.0 RSR, deploying the formidable machines across prestigious championships throughout Europe and North America. Privateers dominated the European GT Championship, the IMSA GT Series, and the fiercely contested Trans Am Series, utterly overwhelming rival factory programs through unmatched mechanical durability and pace. At the 24 Hours of Le Mans and the 12 Hours of Sebring, customer RSRs consistently punched far above their weight category. By outlasting fragile prototypes and decisively dominating the GT classes, these machines established an unprecedented era of sports car supremacy that lasted throughout the mid-1970s. The secret to this enduring dominance lay in the unbreakable synergy between light overall vehicle mass, razor-sharp chassis balance, and relentless mechanical reliability. Where more exotic machinery fractured under the intense strains of endurance competition, the air-cooled flat-six architecture proved virtually indestructible under the harshest operational conditions. From club circuits to international endurance monuments, the competition pedigree established by the RSR program permanently redefined Porsche brand identity. It proved that a road-based sports car architecture, when honed to absolute engineering perfection, could master the most grueling racetracks on the planet with complete and utter authority. The heroic transition from the street-legal Carrera RS 2.7 to the track-dominating RSR dynasty remains an immortal chapter in automotive lore. Through sheer mechanical brilliance and relentless competitive courage, these legendary machines forever established the 911 as the undisputed, definitive sports car benchmark of the modern racing era. The commercial reality of the Carrera RS 2.7 permanently transformed Porsche corporate destiny, shattering initial conservative sales forecasts by ultimately reaching an astonishing total of 1,580 units built across 3 distinct production series. Surpassing the critical 1,000-unit threshold allowed Porsche to successfully homologate the vehicle for FIA Group 3 Grand Touring competition, cementing its structural dominance across amateur and professional grids, while proving that an uncompromising, track-focused machine possessed massive commercial viability. This unexpected market triumph completely revolutionized executive thinking inside Zuffenhausen, proving that passionate sports car purists were eager to pay a premium price for uncompromising lightness, razor-sharp mechanical responsiveness, and stripped-down engineering, rather than conventional leather-lined grand touring luxury. In doing so, the 1973 RS established a permanent engineering philosophy that would guide Weissach for the next half-century, creating a sacred design blueprint founded upon 4 non-negotiable pillars: natural aspiration, fanatical weight reduction, aerodynamic functionalism, and unadulterated driver involvement.
The commitment to high-revving, naturally aspirated flat-six power plants became the acoustic and mechanical heartbeat of every subsequent Rennsport model, prioritizing instant linear throttle response, razor-thin rotational inertia, and an intoxicating high RPM crescendo over the muted complexity of artificial forced induction systems. The relentless war on excess curb weight, pioneered on the Carrera RS, also established an uncompromising precedent, teaching generations of Weissach engineers that shedding structural mass improves every conceivable dynamic metric, from high-speed directional agility and braking distances to fundamental tire longevity. Aerodynamic functionalism, validated by that iconic upswept Ducktail spoiler, became an indelible law of Porsche design, ensuring that future performance aerodynamic devices were never added merely for dramatic styling, but existed exclusively to generate stabilizing downforce and direct vital cooling airflow. Above all, the Carrera RS placed the human driver at the absolute epicenter of the mechanical experience, providing unfiltered steering fidelity, tactile pedal placement, and telepathic chassis communication that transformed driving from a passive task into an electrifying, visceral dialogue. This potent engineering formula lay dormant during the late 1970s and 80s until 1991, when Porsche revived the legendary badge with the 964 Carrera RS, stripping out modern soundproofing and installing a seam-welded chassis with cup-derived suspension geometry. Powered by a potent 3.6-liter flat-six engine producing 260 horsepower, the 964 RS channeled the raw spirit of its 1973 ancestor, featuring magnesium cup wheels, lightweight aluminum body panels, and bare-bones interior door pull straps. In 1995, the final air-cooled evolution arrived in the form of the revered 993 Carrera RS, featuring an enlarged 3.8-liter engine equipped with the innovative VarioRam variable induction system and lightweight mechanical valve train technology. The 993 RS and its track-focused Club Sport variant refined aerodynamic downforce with adjustable biplane rear wings and deep front splitters, perfectly continuing the functional downforce ethos originally pioneered by the aerodynamic testing on the classic 1973 Ducktail. When water-cooled technology transformed the 911 architecture at the turn of the millennium, Porsche preserved the spiritual core of the Carrera RS by introducing the legendary GT3 moniker, engineered directly under the visionary direction of motorsport boss Andreas Preuninger. Featuring the race-derived dry-sump Mezger flat-six power plant, the 996 GT3 honored the Type 911 83 engine heritage by refusing turbocharging, revving relentlessly beyond 8,000 revolutions per minute and delivering pure motorsport durability directly to public highway drivers. The subsequent 997 GT3 RS generation expanded the envelope even further, introducing ultra-wide composite bodies, carbon fiber aerodynamic wings, dynamic drivetrain mounts, and titanium exhaust systems that shaved vital grams while generating race-grade downforce across high-speed sweeps. As material science evolved into the modern era, the 991 GT3 RS adopted magnesium roof panels, carbon fiber front fenders, and active aerodynamic louvers, directly echoing the radical lightweight sheet metal and Glaverbell glass experiments of 1972. Today, the Extreme 992 GT3 RS represents the apex of this continuous lineage, deploying central radiator cooling, Formula One-derived drag reduction systems, and multi-element carbon aero surfaces that produce over 800 kilograms of crushing downforce. Yet, despite decades of rapid computational progress and advanced active chassis systems, every modern GT Porsche traces its fundamental mechanical soul directly back to that pioneering 2.7-liter homologation special born during an uncertain corporate era. The Carrera RS 2.7 stands immortal as one of the most revered and coveted automotive icons ever conceived, an undisputed benchmark of functional beauty that permanently established Porsche as the undisputed master of road-legal competition machinery. More than just a legendary historic vehicle, the 1973 Carrera RS created an everlasting engineering religion, ensuring that as long as sports cars exist, the uncompromising pursuit of lightweight purity, natural aspiration, and visceral driver emotion will forever reign supreme. Thank you so much for joining us on this deep dive into the legendary engineering and heritage of the Porsche Carrera RS 2.7. If you enjoyed discovering the secrets behind this iconic flat-six masterpiece, please take a moment to give this video a thumbs up. Be sure to subscribe to our channel and click the notification bell so you never miss any of our upcoming technical documentaries exploring the world's greatest engines, supercars, and racing legends. Your support fuels our dedicated team to create higher quality content. We would love to hear your thoughts on the Ducktail Carrera, so please share your perspective, favorite details, or personal experiences down in the comments below. Thank you for watching, drive safe, and we look forward to seeing you in our next feature.